So far, we've seen that this electric potential should be much easier to calculate than electric fields. What I'd like to do now, and we've also given formulas for calculating it. What I'd like to do now is to see what uses we might be able to have for this electric potential. So there are a few uses. Now, the first use is a little simpler. That's why we'll begin with this. But this is uses for the electric potential. The first use is actually to calculate voltages. We can see this as follows. If we go to the mechanical version of things, for instance, right? If we want to think about the work it would take for us to move an object from point A to point B, you see that in terms of potential energy, that's going to be the energy that it ends up with, U, at location B, minus the energy that it started with, U, at location A, because then that must be the amount of work, energy we had to put in to carry the object from A to B. There's a quick proof of this, if you like. The proof would go something as follows. If we want to know, for instance, the potential at location B, right? All that we would have to do is remember that this is the work done by us to take the object from our reference point and to locate it at location B. But that amount of work can be broken into two steps using our path independent property. The first step would be for us to take the object to location A from the reference point, and then for us to do the additional work needed to take the object from A to location B. Now, if you look at this equation here for a moment, you will recognize that this first term is actually the very definition of the potential of the object at location A. And now I can take this equation here and solve for the work to go from A to B by subtracting UA off of both sides. So therefore, I conclude that the work done by us to move the object to B from location A is just going to be subtracting this from both sides. On the other side, I had the potential energy at location B, and now I just subtract off the potential energy at location A. All right, well, that's a simple enough result. The beauty of this thing is that we could see this kind of intuitively here in the mechanical case. The electric case, and we've actually proved it, the electric case actually follows directly because now all we have to do is divide everything through by charge. That's this constant theme in the electric case. So for the electric case, I would divide through by the charge, right? And think about then the potential energy per unit charge at my various locations when I'm thinking about specifically moving a charge around in my system. And that equation then becomes, because work per charge is the voltage, so this would be the voltage going from point A to point B is going to equal, and this is the definition of the electric potential. It's potential energy per unit charge, so that is V at B minus V at A. So if I want to calculate a voltage, all I have, and I happen to have the potential, the electric potential, it's simple. The voltage between 2 points is just the difference in the electric potential at those points. That is why sometimes we say that voltages are potential differences. They are differences in potential. Okay, so that's our first use. we can quickly calculate voltages if we happen to have the potentials. Okay, now the second use is even more exciting. The second use actually allows us to use this property that we've just proved to enable us to actually extract the electric fields from the electric potential. And because electric potential is easy to calculate, if we can extract electric fields in an easy way from electric potential, we can calculate, this gives us a new way to calculate electric fields. So let's give this a try then. So let's see what happens. Can we get at this use number 2, which would be to calculate electric fields. Now, this idea works as follows. The basic premise is, let's see what happens if I consider some point here x, right? And then what I'm going to do is consider a neighboring point that's moved over from my point x by some distance delta along the x-axis. So the new location will be my original location plus a displacement of size delta, but it's going to be, say, along the x-axis in my first example. So it's going to be multiplied by a unit vector I hat. So what I'm going to be doing then is calculating this potential difference as I go from x to this location, x plus delta. Very good. Well, I know from the theorem that I've just proved that the potential at this new location, x plus delta times I hat, minus the potential at my original location, is simply the voltage between those two locations, x plus delta I hat, getting there from location x. The reason why I want to look at it this way is that this voltage then I can relate to an integral. That voltage we know is minus, because it's always work done by us, so that's minus the integral of the electric field at x dot dx as I travel along my pathway here from the point x to the point x plus delta I hat. Now here is, this is a dx vector. Here now is where we're going to use a little bit of our knowledge about vectors. I'm going to choose the path that I've shown you here, which is straight out along the x direction. So each of my little displacements, dx, these little displacement vectors, notice, are just tiny little distances, which I might call dx's, right? And they have those tiny little lengths, but they all point exactly in the I hat direction, along the x direction. So here, if you want, I'll draw a little I hat vector to remember us of that particular direction. So it's dx times I hat. So let's substitute in that vector nature. So it's minus integral x all the way to x plus delta times I hat. Now I have E, the electric field at each of these locations, dotted with now dx times I hat, or it's going to be a little more convenient, I can write it the other way. The direction I hat times the length dx, so dotted with I hat times the length dx. And I'm writing it this way because this is a very interesting quantity. If you think about dotting something with I hat, all that does, right, is pull out the I hat component of that vector, its projection onto I hat. If you want to work it out for yourself here in terms of components, imagine I rewrite the electric field as the x component of the electric field times I hat plus the y component of the electric field times j hat plus the z component of the electric field times k hat. And remember now how dot products work. You just take the x component, the y component, and the z component, of each of your two vectors, multiply them together, and then add. But the I hat vector has components 1 in the I hat direction, plus 0 in the j hat direction, plus 0 in the k hat direction. So when I take these dot products, I get ex, the x component of e, nothing from the y component, nothing from the z component. So what I'm really doing is I'm actually just integrating here along this pathway between these 2 points minus the integral of x to x plus delta I hat of just the x component of the electric field at these various positions times dx. Okay, now here's my trick. You notice I'm getting this potential difference now to be something very closely related to just the x component of the electric field. So this gives me a way I can actually get at the x component of this electric field. To complete this proof, what I want to do now is play a little bit of a trick. You'll notice this thing here is starting to look a little bit like a derivative. The trick I'm going to play is to take the limit that delta here is going to vanish. So I want to consider what happens now in the limit as delta gets very, very small. Now, when I do that, if I can see my vector diagram here a little bit, if I shrink delta down to a tiny distance, right, I'm not actually covering a very wide range here as I do my integral. So basically, if I can always make this thing small enough so that the electric field is practically constant across this distance. And if it's practically constant across that distance, I can simply pull out the electric field. And what I will be left with then is my minus sign, the x component of the electric field. Now, its value is the same at all of these points here if I'm shrinking delta down to 0. So I'll just pick its value at one particular point since they're all almost the same, namely the point x. So this is the x component of the electric field at my initial point here, x. And then I'm left with the integral of dx from my 2 points, x and x plus delta I hat. But this is just the length of my little path. And the length of that path, of course, is just delta, the displacement that I was using. So this whole integral then just becomes delta. So my result at the moment is minus the x component of the electric field times the width delta. Now this should start to look very intriguing to you, because I see something here that when I solve for this EX should start to remind you of a certain mathematical operation. Let's write this out here very carefully. So I'm going to solve for the X component of the electric field. And to do that, notice I have to bring a minus sign to the other side of my equation. I also want to divide both sides here by delta. So there's going to be that minus sign I was just talking about. I'm going to have a numerator. My numerator is this difference up here, which is the potential at x plus delta I hat minus the potential at x. That whole quantity then divided by delta. Let me draw a little dividing line in here so we can see what we were doing. And now notice this whole quantity here is supposed to be calculated in this limit as delta goes to 0. Well, if I look at this in the limit as delta goes to 0, what I'm looking at right here is the definition of a derivative. Now, it's a particular derivative because I'm looking at the voltage, right, at two different points, and the only difference between these two different points is that they have different coordinates in the x direction, right? I was only moving along I hat. Only the x component is going to be different. If I were to write this out in terms of components, for instance, the first value would be v. His x component has a delta added on, so it would be x plus delta, but I haven't moved along y or z. The next potential here would just be the potential at the point x, y, and z. This whole thing is divided here by delta. And in that limit, I hope you are noticing this really is exactly the definition of a derivative, but it's a derivative when you are only allowing yourselves to change x. In other words, that is a partial derivative. So I would just take the partial derivative of the potential, in this case with respect to x, and that then would give me the electric field at x, the x component of the electric field at the corresponding point. So I hope you can see, I'm going, and I'll allow you to do this as an exercise, that I can carry this argument out by moving not just along the x direction as I happen to do here, but if I did it along y, I would be looking at changes in v along y, so that would then become a partial y derivative. But because I'm moving along y, when I do my dot product here, I will be getting the y component of the electric field instead of the x component of the electric field. So there would be two other equations. They would tell me that the y component of the electric field at my given point I would get by taking the partial derivative of the potential in the y direction, and the z component of the electric field I would get by taking the partial derivative of the potential with respect to the z coordinate. Now, you might recognize this kind of a situation from your vector calculus class. There's a compact notation for representing this kind of a derivative. This is really nothing other than the gradient of the potential. So another way we could write this all more compactly, how it's normally written, is you would say, okay, the electric field I can get by taking minus del, right, which is a vector operator, I'll define it in a moment, of the potential. Where now the definition of this del operator is as follows. What you simply do, you remember this from your calculus class, is you do I hat times the derivative in x plus j hat times your derivative in y plus k hat times your derivative in z. Now, the beauty and the use of this result is as follows. As we had already commented, calculating the potential is a much easier job than calculating the electric field. There's no trig, there's no Cartesian form, there's no 1 over r cubed, or something to the 3/2 power. There's none of that. It's just a simple scalar value that you have to integrate. And what this formula tells you then is that to get the electric field, you can get back all of your vector nature of that electric field and do all of that calculation, but no more sines and cosines. Now you just have to take this gradient. To get the components of your electric field vector, it's as simple as simply taking a couple of partial derivatives. So that's a very powerful result.